So, having done the convergence of sequences and monotone convergence theorem, we have now defined, we are now in a position to define the subsequence of a sequence. Let sequence xn be a sequence of real numbers and n1 less than n2 less than etc. less than nk etc. be a strictly increasing sequence of natural numbers. The corresponding terms of the sequence xnk given by xn1, xn2 etc. is what is called the subsequence of sequence xn. That means, the subsequence is formed from the terms of the sequence itself, and the order in which the terms appear in the sequence is not changed in the subsequence, but it need not be in exactly the same correspondence with the set of all natural numbers. Let us look at an example. We can see that suppose the sequence n is taken, we have the sequence n as 1, 2, 3 etc. We can form a subsequence as the subsequence 2n, which is equal to 2, 4, 6, 8 and so on. Now, how this becomes a subsequence by the definition is that for the original sequence x1 corresponds to 1, x2 corresponds to 2, x3 is 3, x4 is 4 and so on, and in the subsequence 2n we have started with x2, then we have x4, then we have the remaining even terms. Here we have listed out the original terms of the sequence, but when we consider this as a subsequence, this becomes x2 1, this is x2 2, that means these are the x2 is the first term of this sequence, this is the second term of this sequence and so on. So, that is why we are writing it as sequence xnk, where we are running k from 1 to infinity. So, xn1 corresponds to some element xn in the original sequence, xn2 corresponds to an element or a term after xn1 and so on. So, that is why the ordering of the terms of the sequence is important while considering the subsequence as well. So, that is why we have n1 less than n2 less than etc. less than nk to be a strictly increasing sequence of natural numbers. Then we have xnk is a subsequence of sequence xn. Now, what is the relevance of such subsequences? Because we can see that a sequence converges if and only if all the subsequences will converge to the same limit, or in other words, this defines a divergence criteria for sequences, namely we have a sequence xn converges to any element x in R, then any subsequence xnk of xn also converges to the same limit x. So, that is what we discussed previously. The subsequences ensures the convergence of a sequence. So, let us prove this result. The proof of this theorem is as follows. Proof. We have started with a sequence xn and it is given that x is the limit of this sequence xn. So, by the definition of limit of sequence, given epsilon greater than 0, there exists some natural number k such that modulus of xn minus x is less than epsilon for every natural number greater than or equal to k. And so this condition is given already because x is given to be the limit of xn. Now suppose we have a sequence xnk. As we have discussed in the previous example, we can see that the subsequence can be considered from anywhere in the original sequence, and as we move on, the terms should be on the right side. So that means here x2 was the first element of the subsequence, whereas x1 is equal to 1 is the first element of the original sequence. So the first element of the subsequence is definitely not the first element of the original sequence. It need not be always. So the first element of the subsequence will be somewhere like the third element, fourth element or fifth element or so on. So we are going to claim that if this is a subsequence, what are we going to claim? We are going to claim that nk is definitely greater than k. So the proof is obviously by mathematical induction. Suppose we have n1, we know the first suffix of the subsequence will be definitely larger than 1. That is why we have stated using this example, because we have taken the suffix to be 2. So x2 is the second element in the original sequence. So that is the first element of the subsequence. So 2 is the suffix corresponding to n1, 4 is the suffix corresponding to n2, and so on. So we can see that n1 is definitely greater than 1, n2 is definitely greater than 2, and so on. Likewise, we have n1 is definitely greater than 1 because we are starting the subsequence from some point on the sequence. Now assume that say np is greater than p. We are going to see what is np plus 1. So np plus 1 will be equal to np plus 1, and therefore this is greater than what? P plus 1 definitely, because this is obviously greater than, and p plus 1 is obviously greater than np plus 1, and so that is definitely greater than p plus 1, because we are having the p plus 1th term in the subsequence. That is definitely greater than the pth term plus 1. This is the suffixes that we are dealing with, and that is definitely greater than p plus 1, and this shows that nk is greater than k for every natural number k. Therefore, by our assumption of a limit modulus of xn minus x is less than epsilon for every n greater than or equal to k is valid for nk as well. That is, we can replace your xn by modulus of xnk minus x is less than epsilon for every nk greater than k as well, which shows that the sequence xnk of subsequences also converges to the same limit x. So that completes the proof of the theorem. So that is exactly what is said in the theorem. If a sequence xn converges to x, then any subsequence that you have in the sequence also converges to x. And as we discussed, this gives us a divergence criteria. We can see the divergence criteria. A sequence xn of real numbers diverges if it satisfies either of these two conditions. The first being two convergent subsequences have different limits, or sequence xn is unbounded. Why these two conditions is because we have already seen convergent sequence is always bounded. So, convergence implies boundedness. Therefore, if P implies Q, we know that negation Q implies negation P. Therefore, negation Q implies negation P. So, we have not bounded implies not convergent, because convergence implies boundedness we have already seen in the previous session. So, not bounded means it is not convergent. That is why we have one divergence criteria to be the sequence to be unbounded, and the second one is, suppose you have two different subsequences which converges to two different limits, definitely that contradicts the theorem 1 that we have just now seen. That is theorem 1 that we have just now seen. If sequence xn is converging to any x, then whatever be the subsequence that we are taking, that also should converge to x. So, if we have two subsequences which converges to two different limits, definitely the sequence cannot converge to the single point x. So, we can see an example to illustrate that. Consider the sequence say 0, 2, 0, 2 etc., which is definitely bounded because every element is less than or equal to 2 and greater than or equal to 0. Therefore, 0 is less than or equal to xn less than or equal to 2 for every n, and hence it is bounded. So, it does not satisfy the divergence criteria that the sequence is unbounded. But does the sequence converge? Let us see. Define a subsequence xnk where nk is odd. Nk is odd, and another subsequence say x tk where tk is even. Then we have the first subsequence having only the odd suffixes, and therefore, we will be having this sequence entirely equal to 0. So, it is a constant sequence, we will call it. Sequence xnk is the constant sequence 0, 0 etc., whereas sequence xtk is 2, 2 etc. So, we can see that the same sequence given has two subsequences. One is a constant sequence, and so this converges to 0, and this constant sequence converges to 2, because whatever be the value of n, as n goes to infinity, this is not going to change. This is going to 2 itself, and this goes to 0 itself. So, we can see that the two subsequences that we have here, one converges to 0 and the other converges to 2. So, which shows that two subsequences have two different limits, and hence it is not convergent. Therefore, the given sequence is not convergent. So, that is the divergence criterion number 2 that we had, condition number 1 that we had, and this we have already discussed. So, these are the two conditions that we have. Next important result in real analysis is what is called monotone subsequence theorem. This theorem says that every sequence of real numbers has a monotone subsequence. Whatever be the nature of the sequence that we are taking, it has a monotone subsequence. So, whether the sequence is convergent, whether the sequence is bounded, whether the sequence is divergent, whether the sequence is monotone, whatever it be, every sequence of real numbers do possess a monotone subsequence. So, the proof is like this. It is an interesting proof, the proof of monotone subsequence theorem. So, we have, suppose sequence xn is a sequence given, then we know that it is a function on the set of all natural numbers. So, here you have 1, 2, 3 etc., and then the elements may be something listed like this. So, we can define something called the peak of this sequence, peak. So, what is the peak of this sequence is, an element xm is called the peak if xm is greater than xn for every n greater than or equal to m. So, that means whatever be the natural number that follows m, xm should be greater than xn. That is why it is called the peak. So, here in this example that we have drawn, we can consider this as the peak. Why? Because after 3 or after this whatever number this be, let it be m. So, after m we can see that for all the other natural numbers, the terms of the sequence are lying below this number. So, this can be considered to be a peak. So, for any sequence we can define such peaks. Now, two cases arises. Case 1, suppose the sequence xn has infinitely many peaks, infinite number of peaks. Then we can order or we can arrange those peaks as say xm1, xm2 etc., where if m1 is larger than m2, larger than etc., we will have xm1 to be less than xm1, m2, less than xm3 and so on. So, but what we require is, in order to be a subsequence, we need a monotone subsequence, right? So, in order to be a subsequence, we need an increasing terms. So, what we do now is, we will take m1 less than m2 less than m3, we are going to arrange these numbers in an increasing order. So, these mk's is an increasing sequence of natural numbers. Correspondingly, what happens is, because xm1 is a peak, xm1 will be larger than xm2, xm2 will be larger than xm3 and so on, otherwise they cannot be peaks. So, we are having a monotonically decreasing sequence of elements which are in fact elements of the original sequence xn. That is, we have now created xmk to be a monotonically decreasing subsequence of sequence xn. So, we are done, because what we required to prove is that if we have a sequence xn, it possesses a monotone subsequence. So, xmk now becomes a monotonic decreasing subsequence. Now, consider the next case, that is, suppose it has only finite number of peaks. So, case number 2, let sequence xn has only finitely many peaks. So, we can arrange those peaks as say xm1, xm2 etc. up to some xmr. After that, there are no peaks. Now, consider n equal to or n1 equal to mr plus 1. Then definitely xn1 is not a peak. So, if xn1 is not a peak, it means that there exists at least one element n2 which is the smallest. At least means we can have a collection of elements, maybe we take n2 to be the smallest of them, n2 such that xn2 is larger than xn1, because xn1 is not a peak. So, there definitely exists a larger element, say xn2. And since xn2 is not a peak, again the same can be applied to xn2 is not a peak. So, this can be done infinitely many times, and then we get a sequence of numbers, say sequence xnk, which are all elements of the original sequence xn, and this is monotonically increasing subsequence of the original sequence. So, that is how we can form a monotonic increasing sequence of non-peak elements, and we will be showing that this has got a monotonic increasing subsequence. So, that completes the proof of monotone subsequence theorem. And we have another very important result that we have to learn, which is called the Bolzano-Weierstrass theorem. A bounded sequence of real numbers has a convergent subsequence. So, we have seen that convergent sequences are always bounded, and we have seen in a counter example that all bounded sequences need not be convergent. We have seen an example 0, 2, 0, 2 and so on, and bounded sequence need not be convergent, but we can show that, or Bolzano and Weierstrass showed that bounded sequence of real numbers do possess a convergent subsequence. Let us see the proof of it. Suppose we have sequence xn to be bounded, therefore, sequence xn can be considered to be inside an interval AB. We take I1 to be the interval AB, and we bisect the interval I1 into two parts, namely I1 prime and I1 double prime, and using that we classify the elements, say A1 equal to the set of all natural numbers n such that xn belongs to I1 prime, and B1 equal to the set of all natural numbers such that xn belongs to I1 double prime. Then definitely one of these contains infinitely many terms. So, if A1 is infinite, we take I2 is equal to I1 double prime, I1 prime, sorry, and if A1 is only finite, definitely B1 will be infinite, then I2 will be equal to I1 double prime. And we will continue this process so that we get a collection In of nested intervals, In containing In plus 1 for every n. So, this is a collection of nested intervals. Also, we have, yes, here we have to take n1 equal to 1 and n2 to be the least element such that xn belongs to I2. So, whatever be the choice of I2, we take n2 to be the least element such that x2 belongs to I2. So, likewise we get a sequence xn k of monotonic increasing sequence.